Tesol is the largest silicon and system engineering solutions company. Under one roof, we offer end-to-end engineering platform for chip design, test product engineering, embedded systems, and PCB hardware design. We have enabled several companies worldwide to design and accelerate time to market for several cutting-edge products in automotive, industrial, IoT, and consumer domains. With over 3,000 employees worldwide, we have a global footprint spanning across over 10 countries in North America, Asia, and Europe. You can leverage our state-of-the-art infrastructure in EDA tools and silicon bring-up labs for your product development needs. We have state-of-the-art ATE equipment in our test labs and qualification labs in Bangalore, San Jose, Austin, Singapore, and Penang. Over the last 18 plus years, we have evolved to be a trusted partner and truly an extended engineering arm for all our customers. Please reach out to us for your silicon and system engineering needs, and we look forward to partnering with you.
So today is our next DV Club in Europe, where a focus on artificial intelligence and machine learning in verification. It's a topic that's been requested by many people. Okay. Again, we're still fully remote for DV Club, although obviously our verification futures is also face-to-face. So there we have 146 attendees representing 85 different companies across 28 different countries. Okay, we have two speakers. We're going to run for an hour, and as if you've attended before, you know that we're very strict on the timing. Our first speaker will be Rajendra Prasad from Infineon Technologies, and then Daniel Hansen from Cadence Design Systems. Okay. Thank you to our sponsors, Agnesis, Cadence, Brecker, Impress, Synopsys, ARM, and STR. When we go back to physical meetings, they host for us, and of course Tesol, who's my employer. Okay, thank you. So at this point, we'll hand over to Rajendra, or Raj as I know him, and as soon as you share your screen, Raj, I'll do the introductions for you, okay? Okay, thanks. So, our speaker today is Rajendra Prasad from Infineon Technologies UK Limited, where he's Head of Verification. The title of his talk is Smart Adaptive Algorithm. Rajendra has 20 plus years of experience in verification. He started his journey as architect for 8 and 16-bit microcontrollers. He then moved to front-end design for hard disk drive applications, followed by verification of TriCore, the CPU that is used in Aurix products at Infineon. He currently is the head of verification at Infineon in Bristol, where he is located. Over to you. Thank you, Raj.
Thank you, Mike. So we are going to talk about smart adaptive regression using nearest neighbor algorithm. So I will just first give the motivation behind this topic, and then we will dive into the implementation details and also how it is actually useful in our real life job actually. So facilitating the qualification of design and verification changes by the DV teams on daily basis, especially when you are looking at a large IP or subsystem verification, is very demanding. So basically engineers work on various subblocks of an IP or a subsystem during the development phase of the project, as we all know from both the design and verification teams. So if you are working on a small block where your regression, the full regression itself takes an hour or two, then that's absolutely fine. So everybody, when you're making changes in the design and verification team, you can run in a quick regression and then you can qualify them. But when you're talking about, that's why I have highlighted here large, especially, so which means like a big CPU design or like big system subsystem that you're talking about when you're designing and verifying with a team of, let's say for example, you have 10 design engineers and 15 to 20 verification engineers on a big large IP block development. So your regression itself is going to take overnight or like even more every day. Yeah, so you have got people working on various design sub blocks of the large IP, and then the people will start to commit. So that means that each and every commit or the check-in that you call it in the clear case world is going to influence the whole bigger picture of the entire regressions. And also there will be people working, engineers working on various topics or design subblocks on a daily basis. So multiple commits from different design and verification team members without right qualification regression. So that means that you have to, when you are checking in something, when you're committing something, you have to qualify that your changes are good and they do not break anything else. So that's why you need to make sure that the quality of your commits is very high. So if they are not, if something is committed without the right qualification, then the whole cycle of project development will increase. That increases the debug time, as we know, and also it directly impacts the project schedules. So there is a small diagram illustration here, so that I just want to describe the problem statement. So let's, for example, on day one, so you have got the changes going in, say, for example, D1.1, 1.2, 1.3, and 1.4. So imagine that you have got a qualification regression. A qualification regression ideally is supposed to be, let's say, for example, a 45 minutes or 1 hour regression where you can quickly qualify your changes, because you cannot run every time for every commit. You cannot run a large regressions, which is not, we cannot ask the design or verification team to do that. It's not feasible or practical. So imagine you have got a set of regression where it covers pretty much all features basically, and then if you have a commit which is very buggy, which is say D1.4, and then that is committed into the system, and then overnight regression tells you that something is terribly broken, and you haven't then you have a regression failure overnight. So next day morning you come back and then see that, okay, so something has gone wrong. Now you have to go and debug what happened, and then you realize that, okay, so you have got a buggy commit here which is 1.4. So there are two effects in here. So first thing is that all the changes which went in on that day one, the other 1.1 and 2, 3, they were not qualified correctly. Yeah. So and then the next day, it's the engineers will continue to work. So that means that next day, so the bug in the 1.4 is fixed. So and the next day people will commit again. So from various teams, and once that one is, if any of that one is buggy, then you will immediately follow on day 3. So you have got 3 commits, let's say for example 3 from day 1 and then 3 from day 2, which were not qualified at all. So now you do not know whether the actual problem is coming from the day 1 commits or day 2 commits. So this is a real practical problem that we have faced, which will increase the overall debug time and increase the project schedules. So that is why, without the quality of the qualification regressions that we are talking about is very, very important to close the loop. So why is it so essential? So it means that, because why you can't extract a good qualification regression all the time, because there are different views of verification and design blocks. So you have got 10 design blocks and various different views, which means you have got the UVCs around your verification infrastructure, around your test design, inside your test bench, and each and every view of the functional and design blocks are different. And also it is unreasonable to ask anyone to extract the tests based on the changes which are being made. If one person is working on one block, then the test database changes, people will add more tests and changes will happen. So it is not practical to expect someone, especially the design team, to know what are all the tests that will specially stress their own blocks. And it's not only just their blocks, but the interconnected blocks, because the whole system is connected together, and you have got design blocks and verification blocks of different nature. Some of self-contained blocks, some are the self-contained blocks, and some are the blocks which are heavily dependent upon the interconnects, which are connected to the blocks in the forward and backwards. So there are various types of blocks which you can encounter in the design and verification side as well. Yeah, so and also it is unreasonable, it's not feasible for every user to expect what are your connected blocks and how those blocks are being influenced by your changes. So that is why it is, so we have developed a regression flow to extract high quality of test suite for a qualification regression. So typically we, the regressions, so the smaller regressions take overnight, but the larger regression sometimes take a weekend, because if you're talking about a large IP, like for example TriCore. So so we have developed this tool to extract the high quality test suite for a qualification regression based on the changes made by the individual design on verification engineer. So that means if someone is changing a block A, you're not going to run tests which are covering the block, say for example K or Z, which is very far from the changes that you are making. So it is very important that if someone says that, okay, I've changed this block, there should be a tool, there is a tool which gives you the tests which are rightly suited for the changes that you are doing. So that is the motivation behind this. So basically the tool that we have developed here is completely transparent, so which means it takes various parameters and factors into consideration, and that makes it project independent. So that means it is not dedicated for one project, it is a very universal tool. Sorry, somehow it's not jumping to the next screen. So is it okay if I present like this?
Raj, can you make it full screen because it's small?
Yes.
Just go back into
Slideshow. Okay.
Yeah.
Yes.
So I may go back and forth like this. Okay. So I'll briefly describe about the three-phase approach. So what is it that is needed for this one? So the first one is the infrastructure. So you need to build some infrastructure. So which means like what are all the design blocks that you want to choose. So and then what are your functional blocks? So which means the functional verification. What are all your UVCs, and whether you're doing interrupt verification or data transfer verification or your virtualization. So depending upon whatever the functional blocks you're talking about, or the design blocks, let's say for example the data transfer block, load block, or the program fetch block. So like that, so you can distinguish between, so you have got the functional blocks and also the design blocks. So now you first choose your number of blocks that you want to partition your design and verification, and then you can first grade the test. So once you start to build your test database, so the test people want to start to build the test database, which is based on the directed tests or from the random tests. So you can start to grade these tests based on the coverage and also based on the other features. Like for example, if a particular test has found a bug, then you can give more weightage for that feature for that particular test. So that test is more suitable for that particular feature. So you can add like that. Or if a test has found a bug in the from the customer side, then you can add that. So there are various parameters that you can use to grade the test and push the test into the particular feature. Yeah, so that's first one is the basic infrastructure. So basically this infrastructure is something that you can build. The first basic infrastructure can be built, and then it can be improved over a time. So that is the first phase you have to do. The second one is the actual usage model, which is the user. Now I'm the user, so I'm changing some blocks. I'm working on a design block B, and now I say that, okay, I've been working on design block B and I made some changes to design block B. So, or some people can be working on multiple blocks. So I'm changing design block B and design block C. So you give that input to the tool. So now the tool creates some kind of distribution, so which we call it as red dots. So the blue dots are or the tests which are spaced in a multi-dimensional space. So like for example, if you have got 10 design blocks, so I'll just for understanding, I'll use the design blocks. So you have got 10 design blocks. So a test is graded in these 10 design blocks. So that means you have got 10 dimensions here. So a test is spaced in a multi-dimensional space, which is having 10 dimensions. So those are all the tests are placed in this multi-dimensional space. So let's call it as blue dots. And now you have changed something, and then that you give to the tool, and then the tool creates a distribution. So that means that it gives you a kind of red dots. So which means like, okay, so now I have changed a feature. Let's make it simple. So I changed design block B. So my design block is B. So that means that the dot corresponding to the red dot is the distribution is for block B. And now the third phase is to extract the test. So as we discussed, so it is not feasible to run say 50,000 tests for each and every change that is going in by total team of 25 people. So we need to identify what are all the tests which are more suitable for the change this particular designer is doing, which is block B, for example. So now you put a dot there, and then this tool looks into the machine learning algorithm, and then it will, the nearest neighbor algorithm, basically people who are in the AI side would know this very much. So so use that algorithm, and then it finds out the tests or the dots or the blue dots which are closer to the dot that you have placed, which is the red dot. So now you have extracted a certain number of tests. So which means like you are choosing high quality or a good quality test, which will actually stress the change that you are making here. So, and then you run the smart regression, and the tool naturally runs the smart regression, and then it's whether it's a pass or fail. So your commit or your change is yeah, okay, so this works. So let's go to the phase one part. So the knowledge base and the test grading. So knowledge base is nothing but the details and complexity of the knowledge base basically depends upon the design and verification partitioning. So you ideally partition depending on the size of your blocks, or how much of your the verification partitioning that you want to do, how many blocks that you don't want to partition too many blocks at the same time, not too less. So you have to have some kind of reasonable distribution. And then knowledge base should be generated by both design and functional blocks, as we discussed, and the connectivity. So that means like how strongly they are connected, or how weakly they are connected, or whether they are connected at all in the first place. So that type of information that you need to establish, which can be done by so the leads, so the design lead and verification lead. So basic information about how the interconnection of those blocks is done. And the test grading, so the one that we have just discussed, the grading of the test is need to be performed periodically, so based on the selected criteria. So like for example, the coverage, so that is something that everybody can understand, especially on the design world. So if you have your toggle coverage, if you have your block and branch, so you can use any of this, so all those parameters to identify how your how you can grade the tests, and how a test is contributing to a particular block. So now, so just to give an example here, so you have got 10 different design and functional blocks. So let's call it as F1 to F10. So so this is the dependency chart. So now once we provide this information to the tool, it gives you how these blocks are interconnected, this type of connection diagram. So in this particular case, as you know, like F2 is dependent on F1. So that means if you modify F2, so let's say, for example, you are looking into a data path where F2 is modified and F2 feeds into F1. So that means F2 changing F2 doesn't necessarily means that you have to pick the tests which are covering just F2, but you have to check the tests which are influencing the F2 and F1 and even further. So we will see that in the next coming slides. Okay, so the tool already gives you this information. So if you give the name of the feature, it gives you the distribution, so that once you give input the information, it gives you the a chart, bubble diagrams to show you clearly about the interdependencies. So that is the first part, which is the infrastructure building. So to give some information to the tool for test selection. So the second phase is the selection criteria itself. So how do we choose the test? So what is our criteria? So basically, user feeds the features to be qualified and their weightage. So let's say, for example, I am modifying 2 blocks, block B and C. So I think that, okay, so I have my major modification exists in block B. So which means 60% of my modifications are in block B and 40% of my modifications are in block C. So in another, so that's how you have modified. Now I want to extract the tests from the full 50,000 test suite, which will basically stress these changes that I have given. So now how do we do this? So how do we select the tests here? So criteria for selecting the tests is based on how they are interlinked. So like the way we have just discussed. So that if you see this Rubik's Cube, so the test set 1. So that is the test set which is focusing on that particular feature. So if you are changing, say, block B, then the test first set actually covers the block itself. So which means very intensively verifies that block. And then you need to look into the tests which are test stressing the interconnections. So which means, let's say, for example, the next set 2.1 and 2.234, so which are the adjacent blocks. And the ones which are a little bit further, which is at the next level, which is like level 3, which is going further, which means that, for example, 2 is connected to 3. So you change it in 1, and then it goes to 2, and then it goes to 3. So at different levels. So just for an illustration and understanding, so that's how it works. So now assume that you have changed feature 3, and then that has to be qualified. So now the first level, as you can see here, test set 1 is the one which is directly stressing that particular feature, and then level 2 is the one which is test set 2, which is stressing both F3 and F1 and F3 and F10. So this whole thing is based on the diagram, the dependency matrix that we have created here. So the tool will automatically take care of that. And then that is the level 2. So that is how you take these tests, extract the tests. So that means, so this is the phase 2 where you are creating multiple red dots. So that means like so for a change, you can have one red dot or you can have multiple red dots. So that means you can choose the tests which are specifically targeting that particular block itself, or you can, depending on the type of the block and etc., or it can be that some tests from stressing that particular feature and some tests testing the connectivities and at one level, and then at the level 3 at the next level, and also at the next level. So it can go up to any number of levels. The tool can go up to any number of levels, level 1, level 2, level 3, and then it looks into all those interconnected blocks. So here the idea is that you are choosing a qualification regression which is sensible. So you cannot run, as we discussed, 50,000 tests all the time. So I'm going to choose, let's say, for example, 1,000 test regression, which is targeted to stress my changes. So I'm getting the best 1,000 tests, which can run in an hour time, and then I can confidently say that, okay, this is the quality of my change or my modification is good to go into the commits. Yeah. So now test distribution. So now so there are two components here. So the first one is totally, if you say that I have to choose 1,000 tests or 100 tests, for example, then how do I choose these tests? So which means, like, depending upon, let's say, for example, if you are looking into a block which is very much self-contained, a math block or a floating point unit block, then you need to choose the tests which are focused or stressing that particular block. But if you're checking a mux type of or a bridge type of block, then you need to pick the tests which are stressing so many at so many levels, which is level 1, level 2, level 3. So because that block itself is a connectivity block. So depending on the type of the block, you need to choose. So that is where the distribution comes. So that is where we define the weights. So the block, so let's say, for example, a block may have a weak connection to the adjacent blocks, or it may have a very strong connection. Let's say, for example, if you're talking about a math block, that is a very self-contained block where you have a very weak connection, whereas a max block, as we discussed, may have a strong connection to other ones. So yeah, so this is the second part of phase 2. So let's say, for example, you have got total number of tests to be selected is T, depending upon the time you have. So you can say, let's say I can run for 1 hour, or I can run for 2 hours. So then you can choose. So this is the test run time also is something that you can factor into the calculations, but let's not worry about that. But just for the current illustration purposes, let's say you have got a total number of tests. I have given that, okay, I need to choose 1,000 tests. So now how do you choose the 1,000 tests? So now this is a very good illustration of how you can, how the tool automatically distributes the tests at different levels depending upon the type of block. Let's say, for example, here you have a block 1. So let's say it's a bridge or a crossbar type of block. So where it is the main intent of the block is the connections. So that means it is connected to several blocks around it, several modules around it. And then you can say that, okay, the block itself is, the weightage of that block itself is 16%, for example. And then you have got the blocks which are connected to other blocks. They are heavily weighted. So we are talking about these weights here. Yeah. So conceptually, so first we need to establish the connections, how the blocks are connected. That's the level, the first thing. So as long if you give it, the tool will automatically set the connections as a default strength. But if you want your quality of your qualification regression even more, then you will go and then give these weights. So we'll come to how we refine these weights later, in the later part. But whatever is the knowledge that we have, depending upon our information, so you can provide these weights. So those weights are used, so now, to identify how many number of tests that you get. So now if you look into this equation, so if you look into this equation, so what basically it does is, so if you have a block of this nature where you have got interconnections, so that means that it will choose, so let's say out of 100 tests, it chooses, let's say, for example, 20 or 25 tests which are stressing just the F3, and then it's going to choose the remaining, say, 15 or 20 tests from one on this direction and in this direction, and then it will choose tests which are stressing F3, F1, and F2. So it chooses more tests, some more tests in this connections in this direction. So which means you have got some level 1 tests, so 16% of the level 1 tests, and then you have got some level 2 tests and some level 3 tests. Based on this equation, it will find out the number of tests. So basically, you're getting a good distribution. That is the nature of this block. So the block itself is connected to various blocks. So now, if you see a very self-contained block, let's say, for example, floating point unit block or a math, so that itself is a huge beast block. So that means that if somebody changes, then you need to pick up the tests which are very heavily testing the FPU block itself, right? So now there may be some connections because the inputs and outputs it is connected. So all the operands of this math blocks will come in, and then the output of this whole thing will go back into the pipeline. So then that type of connection. So essentially, if somebody changes this one, the main focus of the stress testing should be on the block itself rather than the connection. So it will choose some tests which are connecting, but the main stress happens on that block. So now this whole thing is very much automated inside the tool. So this will give a nice separation from the user what type of test that I want to choose to run. So which so do I run this test or that test, or like what? It takes the whole burden of test selection and the qualification from the whole design and verification teams who are developing a particular project. Yeah. So now comes to the phase 3. So this is the nitty-gritties of the nearest neighbor algorithm. So as I said, this is all the tests which are graded. So if you have 50 features, so we had around 60 features in the functional world. So you have, which means that you have got 50 dimensions in your Euclidean space. So basically, so you need to place a dot inside this whole multidimensional space where the tests are spaced in this space, and it will give you, this algorithm will give you the tests which are, or the dots, or the tests which are closer in the Euclidean distance. So I'm not going to go into the actual mathematics behind this, but yeah, so you can get in touch with me if you need any further details. So I just want to show you some results here. So assume we have 1,000 tests covering, so say 10 features, F1 to F10. And the following diagram actually demonstrates 100 tests based on the changes which are qualified. So this is for simple demonstration purposes. Right, so you have got 10, so which is F1 to F10, and then these are the inputs that you have chosen. So as we discussed before, this may be this could be a level 2 dot or level 4 dot. So which means, like, so you have got, this is actually level 3 dot, as you can see here. So some are level 3s and some are different levels, because F4 is changed 50% and F6 is 30% and F7 is 20%. So this is how the dot is placed. The red dot means that feature 4 is 50 and feature 6 is 30 and feature 7 is 20. And now if you place that, as you can see, the algorithm chooses the dots around it. Again, so there was one common question that we get is that, you know, what does this mean? So this is just a pure representation. So this doesn't actually show, because as you can see here, so there are some blue dots close to it. So because this is a 2-dimensional space, so we are trying to illustrate a multidimensional space into just a 2-dimensional space. So we collapsed multidimensional into 2-dimensional. So that's why this is good for illustrations and understanding. But as you can see, the algorithm picks up the real close dots, close blue dots wherever you place. So basically, as you can see, this one is level 3. This one is 1, 2, 3, 4, level 4, and then this is level 5, as you can see here, which means we can go deep into the level 5. So if a block is changed, which means F1 is changed and then connected to F2, and F2 is connected to F4, and then connected to F6 and F7. So it will automatically choose depending on the nature of the block. All you need to do is that, say that I changed this feature. Let's say my change modifications are in block B, and you go and figure it out. So it goes and figures it out based on the knowledge base. So we look into some results here. So so for the illustration, so as you can see here, so the test database is so these are the dots. So that means depending on the coverage, so the test database is distributed like this. And so the first one, the group A, is the test selection based on the smart regression, and group B is based on the random selection. So either it could be a random selection or it could be a set of tests that you choose. So whichever way it is, so if somebody is changing a feature, so as you can clearly see that the output of the smart regression is giving you the tests in this region, which means the tests which are having high coverage on the feature that you are changing. Yeah, so this is for feature 2, for example. So we'll come to the actual features. I'll map the features, the one F1, F2s, etc., into the actual real features that inside our design for the demonstration purposes. Okay, so so the F2 is here. So as you can see, it's all over the place. So there is no. So let's say in the random regression, you're choosing tests which are not at all relevant to the change that you're doing. So it's not useful, even though you're running, it's waste of simulation time. So this is just a demonstration. As you can see here, different number of tests and how the smart regression tool will go and find out a good test based on the distribution. So so this is the evidence. So there is a particularly so the random selection. So as you can see, from the random selection to the smart selection, there is a huge improvement in every, depending on number of points, cover points here we are talking about. So we have mapped it into the functional for this particular distribution. So in every place, so the overall, you can see the overall improvement of the coverage. So that gives you a kind of good feeling that you are testing the changes that you are actually intending to verify. So this is different versions of the illustration, the improvement of the results. As you can see, the green. Right. So the conclusion. So high quality of qualification regression is absolutely essential for big IP development teams. So where multiple design and verification engineers work on various subtopics or subblocks without much of knowledge on the other domains. So this is very useful for big IP development with big teams. And basically this allows the engineers to detect the bugs at very early phase development. So and hence improving the project timelines. So if somebody introduces a bug in one day, in day one, and that has got a lot of ripple effect going forward in each and every going forward until you properly recover from that bug, and then you want to, then everybody make sure. And also it is the mindset of the engineers as well. Let's say if you have committed, if 4 people have committed changes, and then if the next day morning and we debugged and then say, oh, one person's commit has got a problem, and the remaining 3 people, okay, my changes were not verified very well, so can I move on to my next topic? So they just keep moving on, and then it's very difficult again to trace back once the actual bug is fixed to find out, okay, the second one has caused on day 1 has caused also some problems. So this is so that's why it really helps. So this this particular tool is adaptive. It's based on the changes to be qualified, and also it can add any criteria, like for example the coverage, like scenarios, particular scenarios of the tests, or bug fixes, design tags. So you can use any criteria to tag these tests for selection or to grade them basically. And it's this particular tool has got a very simple interface, and then you can you can build it on basically on its own, and then yeah, so possibility to build and then at the different layers, and then the regrading of this test based on the inputs, user inputs. So yeah, it uses the nearest neighbor algorithm. So the main improvement that we are working with Oxford PhD student is to improve the infrastructure, which is the grading. So the first thing is, like, you know, the knowledge base. So what is the if you have various different design blocks or the functional blocks, you can, people will use this tool, right, over a period of time, and you can use this data, all this data, to learn how the blocks are interconnected and what are the weightages. So it can learn on its own. So now we can eliminate the designer's input as well completely, or the verification people's, or maybe you can give some initial input, and over a period of time you keep running these smart regressions, and you can use the machine learning to learn how the design blocks are interconnected and how much strength they have, so how they interact, how weakly they interact or how strongly they interact, and then you can build the base itself based on the machine learning algorithms. Yeah, so that itself, I think, concludes my talk. So just to give just a couple of minutes information here. So the tool looks like this. I'm not sure, like I need to go into the full mode. Yeah. So yeah, so as you can see here, so this is how the tool looks like. So initially it's starting on a blank sheet. So, and what are all the configurations that you want to build? So you click on it, and then you give that input here, and then it just takes it onto the tool. And then once, so as you can see from the presentation slides, so like what are all the features and what are the weights, initial weights. So you can just use that information and build it. So you can build everything using the graphical user interface itself. So here you can see, like, so the protection system, so the flash interface, so lockstep, so all these blocks which are connected, they have got different connection weights. So we give the initial connection weights. So, and then you click upgrade, and then the tool upgrades it automatically on its own. So, and then it picks up the tests that you choose from, and then it automatically selects a good test. So you building the infrastructure is automatic, and the test selection is also automatic, pretty much. So it just takes the whole burden from the users, both the design and verification team, to choose the tests for the right tests for the qualification. Yeah, I think that's pretty much it. So we have 5 minutes for.
Yeah, thank you, Raj. Yeah, we have a number of questions as well, so it's been proved to be a very popular talk. I guess the first one would be: does the flow suggest tests or tests with specific seeds?
You can put seeds as well. So this is the second information. So you can attribute a seed also for that. So there are few things that we need to remember. So if you're talking about the seeds, the seed might change if your test bench changes. Let's say, for example, in SpecMen or in System Verilog, if you change the seed and if you don't change your test bench components, that seed will give you the exact coverage and the exact scenario. But if you modify your test, or if you modify any of your component, then the seed may generate a different scenario. But if your UVC, let's say, for example, you have an active agent, and if that active agent is pretty much solid and fixed, and you can use the seed itself to give this in this tool, which we are doing already. Yeah.
Okay, that's good. Okay. Another question is, I mean, potentially the connections between
It's the next level that we were discussing. So
yeah,
when you're running over a period of time, because that's perfectly right, because the designers are modifying, the verification engineers are modifying, so the connection strength may vary, but right now the tool is based on the fixed values, but
okay.
the AI tool, the machine learning can be used taking into consideration all the regression results every day when people are running, and then learn how these things are talking to each other.
Okay.
And automatic. So that's our next project that we are working on. Yeah.
Okay. The next question is, who provides the SRF phase 1 data? Is it the person who's doing the check-in? And what sort of data is provided?
So the SRF one is, so that is the building the infrastructure. So
yeah,
you can start building the infrastructure with very basics. So which means I don't have any connections. All I have is 10 blocks. So if you give that basic connection, then that itself is good enough. So that means that there is no level 2 and level 3. So let's say, so here I have got 10 blocks, and I have graded my tests based on those 10 blocks. You are still much better than running some random tests. So which means it will choose, you will have only level 1 at this point of time. And over a period of time, the tool will learn. So that once it learns based on that, once you start running more and more regressions, then it will go and find out when this test is modifying, when this particular feature is changed or is stressed, you have this feature also is being stressed. So that means that there is some kind of connection between these two. So it kind of learns based on various parameters, and it will establish the connections over a period of time, and then your quality of the qualification regression will improve.
Okay. Thank you. Question 3. So, mate, this is the last. Actually, I think we've probably run out of time for questions. So we do have a number of questions that have been asked. Raj, and what we'll do is we'll send you those by email, and if you get time to answer them, that would be very helpful. Okay.
No problem.
But yeah, otherwise it's a very, very good talk. I mean, this is a great application of AI, and I'm sure it's something that people may want to do for themselves as well. Okay. So I'm going to give you a clap, but I'm sure I represent everybody else as well. Thank you, Raj.
Thank you. Thank you very much. Yeah, thank you.
Thank you.